right, so where we've gotten to so far is we've discovered that to describe the wave function for, let's say, a helium atom, it's not enough to simply say it's a 1s electron in the spin-up spin state for electron 1 and 1s spin down for electron 2. We have to take an anti-symmetrized combination of those two functions to make sure the wave function itself is anti-symmetric when I exchange the two electron identities. Unfortunately, however, it turns out this wave function, the way I've written it down, isn't normalized. So just a brief comment or two to understand how to normalize a wave function like this. In order to decide whether our wave function is normalized, we should take the wave function times itself with a complex conjugate and integrate it and see what we get. And hopefully we'll get 1 if the wave function is normalized. In this case, we won't quite get 1. So what that's going to look like is integral of this function times itself. And notice I've written electron 1 in this orange color, electron 2 in the green color, just to help us keep track when we do the algebra. But this integral is going to look like integral of 1s alpha, and I'll drop the 1s and the 2s since my color is telling me that. So 1s alpha times 1s beta minus 1s beta times 1s alpha. Again, remembering that the orange color is for electron 1 and the green color is for electron 2. If I multiply that by the same thing, 1s alpha, 1s beta, minus, in the correct color, 1s beta, 1s alpha. And also keep in mind that I'm integrating over the coordinates of both electron 1 and electron 2, so I should have both an orange integral and a green integral for the integrating over the two different coordinates. This is just a product of two terms, each of which have two terms inside them. So we can do first, outer, inner, last to see what these terms look like. So I've got the integral. The first terms, I've got 1s alpha for electron 1 and 1s alpha for electron 1. And then 1s beta are the terms I've got for electron 2. The outer terms, I have this term times this term. So with a minus sign from here, I have 1s alpha, 1s beta. And then for the green terms, I have 1s beta, 1s alpha. For the inner terms, this term and this term, again, I have a negative sign. So I've got 1s beta from here, 1s alpha from here, multiplying by 1s alpha, 1s beta from here and here. And then finally, the last terms, I've got a negative sign times a negative sign, which gives me a plus sign, 1s beta twice, 1s alpha twice. And now if I step back and look at the integrals I'm doing a double integral. I have to integrate over the coordinates of electron 1 and the coordinates of electron 2. So I can write this is the integral. I've collected the terms so the oranges and the greens are together. And we know what each of these integrals is because we know the original wave functions are normalized. So the integral of any wave function times itself is guaranteed to be 1 because the original hydrogen wave functions themselves were normalized. So this integral gives me 1. Likewise, 1s beta times 1s beta, when I integrate that, I'm going to get 1. On the other hand, if I take 1s alpha times 1s beta, those wave functions are orthogonal to one another. So that integral is 0. Likewise here, 1s beta times 1s alpha, that integral is 0. So if I look at the net result, the first integral is just 1 times 1. The second integral, those are both zeros. The third integral, 1s beta and 1s alpha, those are orthogonal, these are orthogonal, so the third integral gives me zeros. The fourth integral is, again, identical wave functions, 1s beta and 1s beta, 1s alpha, 1s alpha. So here I get 1 with a plus sign. So when I'm done with all these integrals, the final answer is 2. Essentially, since I've written down a perfectly valid wave function but twice, I ended up with a result that was twice as large as I should have gotten. So this wave function is not normalized. Turns out in order to normalize it, all I need to do is stick not a 1/2, but a 1 over square root of 2 in front of it, because that function is going to show up twice. If I throw a 1 over square root of 2 next to each one of these integrals, then when I multiply those 1 over square root of 2's together at the end, that'll multiply the whole thing by 1/2, and that's what I need to normalize the function. So a properly normalized and antisymmetrized version of the helium trial wave function is spin up electron and electron, spin up electron 1 and spin down electron 2 minus the antisymmetrized version of that multiplied by this factor of 1 over square root of 2. And the reason for that 1 over square root of 2 out front is to make sure that our wave function ends up normalized in the end.